Next, I want to talk about experiments that we actually run using CogniCrypt. So this was largely done, no, it was actually exclusively done using the command line version that we have of it to automate these experiments. And I, of course, also want to show you some empirical results that we obtained. So first of all, to facilitate this, we actually wrote Crusoe specifications ourselves for the entire Java cryptography architecture. And for this, we actually also collaborated with a couple of crypto experts from TU Darmstadt. And altogether, these were 42 classes and interfaces. And as you can see here, they cover a number of different areas, right? So key generation, encryption, signatures, hashing, max, and randomness. And what we actually found by looking at these different insurers and required clauses and connecting them, we obtained a very nice picture of the actual API. So I actually found this pretty interesting. I've never seen this published before, actually. So this shows you the dependencies of all the different classes regarding these particular usage constraints. And what you will see immediately is that I found interesting that pretty much everything relies on secure randomness, which sort of makes sense, right? Because if you have any sort of key material or so that is not securely randomly generated, then it can be guessed by an attacker, and then basically everything is falling apart already. So secure randomness is super important for anything related to crypto. Then we have the layer on the bottom, which basically has these high-level objects that are mostly important to programmers, such as a MAC or a cipher, a signature, or a message digest. And then we have these intermediate objects that we have here, so sort of helper objects, right? Like a key pair generator we already saw, or there's also a key store, a key generator, and a secret key factory. And then we have these intermediate parameter objects. So these are the ones that we have colored a little bit more lightly here. So these are just parameter objects, or also here for the second layer, that are provided to these individual objects and that are used by these classes. And yeah, so we had implemented all of this for the entire JCA, the entire Java cryptographic architecture. We have Crusoe specifications that you can also take a look at online if you're interested in. And then we took CogniCrypt with all of these Crusoe specifications, but not with the Eclipse plugin, but rather with the command line version, and we ran it across all of Maven. So actually the entire Maven Central repository at the time. So Maven Central contains mostly reusable artifacts such as frameworks and libraries, right? And back then it was around 2.7 million of them. And we actually ran CogniCrypt over all of them, and it took us only a few days. I actually found this impressive because for 2.7 million artifacts, for some tools, it might take forever to actually run through this. But because we had this efficient demand-driven analysis, we actually were able to complete this within just a few days. And we got the result that you see here, which is actually really disappointing, but still interesting, that in 73% of all these Java artifacts, we had at least one unsafe use, right? So one deviation from the norm, one misuse of the crypto API. And yeah, this is actually, well, I wasn't surprised to see it, but of course it's not a result we would have loved to obtain. And we also wanted to look into a few applications more deeply, and here we chose to actually look into some Android applications. And we only chose the 250 top apps at the time from the banking, health, and password app sector, okay? So these are all apps of which you would hope that they were developed by security experts, or at least with security experts as part of the development team, and therefore we would have dramatically lower numbers of misuses here. But as we ran the analysis, unfortunately, we obtained a result that was rather similar to what we saw before. Wait for it. I should really speed up this animation. But yeah, just to make it exciting. Oh, come on. Now, we then actually wanted to look into some applications a bit more deeply, and for this we actually chose about 250 different Android apps, and these were not just some Android apps, but actually the top apps from the banking, health, and password app sector that we chose back then. And so you might think that these apps had been developed by security experts, or at least with some security champions in their team, so they should hopefully have dramatically better results. But unfortunately, as our results showed, the number was almost identical. 71% of all artifacts also here used the JCA in an unsafe way. And remember, I showed you actually this example here earlier, right, where we had fixed salt and many too few rounds here, and the password based in a string, and so on. So this was actually a real-world application, an Android app that came out of the study, and I can talk about it now because the problem has been fixed. So this was actually in the VR banking app, developed by Fiducia, so we actually had good communication with them in order to get this fixed. They actually were very positive about our findings, so thanks for that. But what's interesting about this app, it's not just a banking app, it had actually also even been certified by TÜV, right? So a German certification body, which is rather famous. And of course, I was very confused, right? So I said, I actually called up the TÜV and I asked them, you know, how could it be that you actually certified this app and they're advertising with it, and you have this really crappy crypto code in there? But they told us that they actually didn't even certify that part of the app. They only certified the 10 scheme that was actually used as part of the app. But of course, if you look at the website, well, you know, they don't really tell you these details, right? That the certification was only about a minor part, and all the rest was actually not even covered. We also found this code, which was interesting. We found a lot more mistakes, right? But this is also a prominent one. This is not a salt, it's an initialization vector for symmetric encryption that is being used down here. And if you know a thing or two about AES and CBC and how initialization vectors are used, then you should also know that an initialization vector should ideally be securely random, so that it can also not be guessed by an attacker. And here it certainly is not. Again, it's part of the bytecode, and that decreases the security of the entire implementation. And this was also not just any app, but this was actually Norton Identity Safe. So this is actually a password vault app by Symantec, and back then it already had about 500,000 downloads in Google Play. And again, we alerted them of this problem, and fortunately it got fixed. So they raised the CVE against this and actually fixed this in multiple versions of their app within just a few weeks. So that was actually also relatively quick. And yeah, if you want to play around with CogniCrypt a bit on your own, I encourage you to download it on cognicrypt.org. Take a look at our Eclipse website. You can download the Eclipse plugin that should give you very easy access to the tool, or you can also just download the the command line version that we have, and we're actually also working on a couple of CI/CD integrations, so you can use it with Jenkins or also other build chains to make easy use of it. And yeah, with that, I also want to summarize CogniCrypt. So CogniCrypt's static analysis allows one to identify misuses of cryptographic APIs as an Eclipse plugin or command line tool. The misuses are identified as deviations from an allow list, right? So you have incorrect method call sequences, incorrect parameter choices, or incorrect object combinations that can be identified. And what's important to this course, the analysis is entirely demand-driven. It combines forward type state analysis, demand-driven alias analysis, backward value analysis, right, for the string and integer values, and a constraint analysis. And the demand-drivenness is really what makes it so efficient and precise, right? So when using CogniCrypt, we have never seen false positive rates beyond 5%. So typically it's a lot less. And also the analysis time is super fast. Like I told you, right? We analyzed entire Maven Central within just a few days. So typically the initial response times, like I also showed you in the video, they're often in under a second. Right, so the video I showed you, that was recorded live. I didn't speed up any of it. Yeah, I already just said that, right? So there's one open point that we have, one open issue. So that is sometimes raising false positives for us, and that is a lack of path sensitivity. So that means that branches are not correlated. We've seen a few cases where people check a certain condition, and because of that condition, the thing that CogniCrypt found cannot actually really be true. Well, dealing with this, it would mean extending the analysis, but it would also likely mean extending and therefore complicating the specification language. And that is something that really has to be thought of, right? Because, I mean, you know, we could always make the specification a lot more complex to cover every single corner case that exists. But then, of course, that's a trade-off, right? And so there comes a point where it might be better to deal with, you know, a couple of false positives in a large project than having to maintain really big and complex and convoluted specifications. Because these also need to be maintained by humans in the end, right? And we need to make sure that these specifications are actually correct and testable. And yeah, so there's something to be said towards accepting false positives in some of these situations. In case you're interested in some further reading, I already mentioned on one of the slides at least this fairly recent journal paper of ours. So this appeared at IEEE TSE. So this is really the paper that gives you most details about Crizzle and CogniCrypt and also our experiments that we ran with it. If you're interested in even more details, you can also access and read Stefan Krüger's PhD thesis, which is, for instance, accessible through my website. That's definitely worth a read as well, and that goes into every single detail you can possibly think of. There's also some related reading that will still become important in the later part of this course. So you saw that we get some very rapid response within the IDE, right? So basically, as you're typing and saving your code, CogniCrypt is already running the analysis and giving you a fairly quick response, so typically within just a couple of seconds. Now, in this case, this typically works because there are only few cases also in large applications, or few locations in large applications that have cryptography code. So the code that we need to scan is actually rather local. But for some other properties that you might want to analyze, you know, outside of CogniCrypt, that might not always be the case. But if you then still want to have rapid response times, it actually helps to implement some prioritization concepts. And that's what we published in this paper on just-in-time analysis. So here we followed an approach where we basically reprioritized the execution of the analysis, in this case based on IFDS IDE, and that basically causes the analysis to give you a rapid response in any case for results that relate to the code you're currently editing or you just saved in your IDE, and other results that are maybe less important to you right now as you're working in the IDE. They get lower priority and they might be reported a little bit later, right? So the analysis as a whole, it might actually run even a couple of minutes, but you're still very likely to get first results and first updates regarding the code that you're currently editing within just a few seconds, right? And that's super useful if you're, for instance, trying to fix a bug, right? So if there's a bug that the tool has identified and you want to make sure that you've really fixed it and it's gone, then using this reprioritization, this just-in-time analysis, you can really get very fast round-tripping times. Yeah, but like I said, I'll get back to this later in this course. I'm looking forward to talking to you then. Bye-bye.